So this video is going to cover two things. The first is going to be a variant of perceptron that we're going to use in our homework assignments, and that's something called MIRA. And then the second thing we're going to cover is the concept of validation as a methodology when doing machine learning. We'll talk about the benefits of it and what the goals of validation are. So that's the plan, and the first part is going to be on something called margin infused, or the margin infused relaxed algorithm. And this is an algorithm that was introduced by Kobe Kramer and Yoram Singer in around 2003, and it's part of a line of research that they were integral in figuring out how to use linear classifiers to do multi-class learning. And we've already seen this. We saw with the multi-class perceptron from the previous video is basically using their notion of how one uses a linear classifier or a conjunction of many linear classifiers, each of which just predicts a binary, or usually just outputs a binary output, and put them into a framework to do multi-class classification. So MIRA, just like perceptron, does online updates to weights. That means that it gets one example at a time, with its label, and then its goal is to then to update its weights or its model based on that one example, and then move on. Throw away that example, stop thinking about it anymore. And the difference between MIRA and perceptron is that MIRA is specifically formulated, that the math is formulated so that its goal is to classify the training examples that it gets with a margin. And intuitive, or at the very high level, that just means that it wants to not just get the right class, but it wants to get the right class such that the correct class's score, is really higher than any other competing class. So MIRA also includes the possibility of adding a cutoff parameter C that avoids overfitting, and we'll talk about what that means. But I'll show you right now exactly what the updates look like. So here is the whole MIRA algorithm. So first we have, these are the update equations, and these formulas are basically the exact same equations we had from the perceptron, where we have the same thing. Let me just remind you about the notation. So W with the superscript of y means the weight vector for the y class, and y is the true class. Y is what we've been given in our training data, and then W superscript f of x is the weight vector for the predicted class, right? So this is the class that our current classifier output. So the key difference between this and what I showed you in the previous video is that we now have these tau parameters, these tau values that, they look a lot like the learning rate that I showed you in the last video, and you can view them that way. You can view them as a learning rate, but the key difference is that this is going to be adaptively set. This is going to be determined by properties of the input example and the current weight vector. Specifically, it's going to be set according to this formula. So this is, what you need to implement for the homework. And if you want to shut off your brain, you're welcome to do that now, but it's going to be helpful to you as a, AI researcher or somebody who uses AI in his or her research to understand the reasons for all these, for these fairly exotic looking equations. So let's look at why these are the updates. But again, if you just want to get the homework done, this is all you need to know. So the idea is that we're going to try to, like I said, make a prediction such that our predicted score for the correct class beats out all other scores, all other possible classes by some non-zero margin, or by a big gap. So here's what that looks like. So again, remember that the classification procedure for this multi-class classifier is that it's going to, this f of x is going to output the class that scores the highest, or whose weight vector gives you the highest score, right? So the argmax. And let's just, for some notational convenience, we'll name this y prime, right? We're going to say that y prime is f of x, is the output, just so we save a few characters. So when we think about what happens when we, um, now that we've defined y prime this way, one thing we can say, because we know that y prime is the argmax, is the highest scoring, right, the highest scoring class, we can say that the score for y prime is at least as great as the score for the true label. So the score on the left for wy prime times x, that's the score for the y prime class, that's got to be greater than or equal to, well, any other the score for any other class, but specifically the score for the true class. Now they could be equal, and they could also be even, they could exactly be the same entity, right, if y prime is equal to y. But let's say for now that y prime is not equal to y. Let's say that we got it wrong. Just like with the perceptron, we're going to say that if we got it wrong, or if we got it right, we're not going to do anything. If we get it wrong, we want to do something. So in this situation, if we got it wrong, then what we're going to want to do in MIRA's motivation is to find a new W such that the opposite is true, right? Such that the score for the true label y is better than the score for this y prime that we thought was really good in this round. So we want this to be true, and we don't just want it to be better. We want it to be better by some noticeable amount, and so we want it to be better by 1, according to what we've written down here. So what this says, right, is now that the score for the true label is going to be greater than or equal to the score for the wrong label, the one that we got wrong, the one that we predicted originally, plus 1. So that's our overall goal, right? Our goal is now to adjust W. We want to change W such that we satisfy this condition. Um, so first off, let's just make sure we understand the condition. So the condition again is just that we want the score for the true label to be higher than the score for what we thought, what we got wrong, the label that we got wrong, plus 1. So we want the score to be 1, at least 1 better than what we originally thought was the right answer. So it turns out that once you have this condition, this inequality that I wrote down here, there's a lot of options. There's lots of W's that that can satisfy this inequality. So we're going to pick the one that's closest to the previous W, right? So that we make the minimal amount of change to W, and that is written down this way, right? So now we have formulated an optimization that we're going to try to solve to get the new W's, right? It's the minimum overall possible W t plus 1s of the sum of the squared distances, from the previous weights. And our goal then is to find the closest new W that classifies the example with a good margin. That's the English way of describing what's in the math down below. Okay, so things have gotten a little bit more complicated, right? Because this looks kind of nasty. It's not the elegant sort of, well, simple update equations that we had before. But at least intuitively, right? Hopefully it's clear what the motivation behind this math is, right? We want to classify with a good margin, and we don't want to move too far from our previous weights. So at this point, it's useful now to recall what our update looked like, right? Our update looked like this on the top left. So we can sort of simplify. What I'm actually doing here is I'm skipping a mathematical step and making the analysis simpler for us. But basically, what we're going to say is that the only free parameter we have is tau. We're going to run these updates the way that they've been prescribed to us, because we believe that, I don't know, because we believe that the perceptron style updates are what we want to do. So if that's the case, then let's think about where these weight vectors can differ from the previous step to the current step. And all we can do, according to the update equation, is update the weights for the true class and the class that we predicted, right? So y and y prime. So when we think about this distance term in the objective function of the optimization, of the minimization, it's summing up over all the different classes the distance from the previous weight vector to the new weight vector. And based on the update equation, we're only going to update two of those, right? So that distance is going to be 0 for all but two of those classes. And the distance for those classes is going to be exactly, tau times x. So we can actually replace this term with this much simpler term to think about. Because all the other entries in that summation are 0, and there's going to be two entries that are non-zero, one of which is going to be minus tau x, and the other one's going to be positive tau x. But since we're taking the square distance, we can just add them up. And since we had this, if we go back, there was this 1/2 there, which was there for convenience. And you'll see what, we see now that why it's convenient, because we get these two tau x's, and we can just add them together, and the 1/2 goes away. So this is a simpler way to think about this minimization. And we can do the same trick down below for that inequality, right? Right now it's written with in terms of wt plus 1, but we know something about wt plus 1. We know where it came from the update equations, again, on the left. So we can just substitute in, for the left side, we can plug in the update equation for the weights of the true label. And on the right, we can plug in the update equation for the weight for the wrong label. So we get this. And all we've done is just plug in that definition, or the update rule that we already committed to. And at this point, we can do a little algebra. So don't be scared that the screen's about to fill up with equations, but basically I'm just doing step-by-step simple algebra. So what we're going to do is let's distribute that x inside the parentheses on both sides of the equation, right? You see how there's a w plus tau x times x. Well, let's just distribute that x into the parentheses, and we get this. And then we can move some terms around, and eventually we can isolate tau, and we get this. So feel free to pause the video and look at these algebraic updates just so you see what I did for each of these algebraic simplifications. But it's pretty straightforward stuff. So we can erase those away because those are just intermediate steps, and we're just left with this. This is the whole optimization now. And this just comes from plugging in the update equations to the original thing that we wrote down, which was the sort of the mathematical translation of this sentence that we want to find the closest new w that classifies the example with a good margin. Well, we defined that with a definition of margin, and then we defined that with the closest being measured by squared distance. And then when we plug in the tau updates, we get this form. So we can actually think about this a little bit more. And when we look at this, right, look at what is this asking us. It's asking us to find a tau that that minimizes this norm. So this norm is tau times x. X is given. X is fixed. It's just some in this setting, it's just the input features. So we don't have any control over x. But what we do have control over is this single scalar parameter, the scalar coefficient tau. And the bigger tau is, the bigger this norm is. So if we want to minimize this norm, we want to get tau to be as small as possible. And we have this inequality as part of the the constraints on the optimization. And basically, if we want to make tau as small as possible while keeping it at least as great as this quantity on the right, we just set tau to that value. Right. So this is where that sort of exotic looking tau setting came from in the MIRA definition. And let me just plug in, throw on the screen the update equations too, and we get this. So this is one version of MIRA. So if you remember back, there was a little bit more going on with the setting of tau, but this at least will do what we want, which is to find a new w that classifies the example with a good margin. And it's really simple because all you have to do is do basically the perceptron step with this adaptive learning rate. Okay, so let's put that aside for a second and think about, let's take a step back and think about machine learning in general. So what I want to talk about is an issue of robustness. So when we do machine learning, what we get is this training set, and maybe it's this training set of digits, um, and we know what the digits are meant to represent. What actual number they're meant to represent, but what we get as input is just these raw pixel values. So we don't know. So we had to learn how to convert from the pixel values to the actual digit identity. So here's a kind of silly classifier that one could design. We could just build a dictionary in Python that just takes all the pixel values in as the key to the dictionary and outputs the true label as the value. So it would look like something like this, right? It would just take in the raw pixel values and do an exact match to any of the data in our any of our training data and um, output the label from our training data. So this is it should shock you that I would suggest this because basically a terrible idea that you would do this. But the weird part about it is that this seems kind of good because you get 100% training accuracy with this, right? If you look at any of the training examples, we will always be able to exactly look up that training example and look up that label from the training data, and we will get perfect accuracy. So of course there's going to be a problem here. And the problem is that when we get a new digit as input, let's say we get this 5 image as input, this 5 doesn't exactly match any of the 5s in our training set. And what's going to happen is we're just going to have to guess randomly on this one. Um, and we'll end up with something like basically 10% accuracy. So, that happens because when you guess randomly in a digit problem where you have 10 possible digits, 1 out of 10 times you're going to accidentally guess the right label. And so this is the worst possible accuracy you get. Um, and that's what's happening, right? We got this weird situation where we got perfect performance on our training data, but really, really bad performance in the future in any, testing application. And what's happening actually is that we're overfitting. We're memorizing the data set that we were training on, and we've basically come up with this very highly complicated model that only knows about the very, very specific examples that we got. So we've overfit. So we can protect against overfitting a little bit, and this is where this extra piece comes in that I left out from the previous slide, or 2 slides ago, um, which is that we don't want to move too far using just one example. So even though our tau computation to figure out how to get a good margin might tell us that we want to set a tau really high and basically move really far in the direction dictated by this one example, we're going to cap that. We're going to say, okay, let's not let that grow bigger than, I don't know, 1. C could be set to 1, which means that for any example, even if you really misclassify it, you're not going to move too far from where you previously were, and that essentially protects against overfitting. But this gives you this extra parameter. So how do we know what value of C to use? And the basic strategy for setting this up is that, right, you don't want to do something. There's one thing that you could do that's very wrong, which is that you could just pick the value of C that gives you the best accuracy on your training data. But then that would be bad because you would probably end up picking a very large C because you want that incentivizes really fitting your training data really well. So what you need to do instead is you need to hold out some data. You need to basically simulate a situation where you're testing, where you're training on part of your data and you're going to test on the rest. So we're going to split our data set into some training data on the left and validation on the right. And what we're going to do is we're going to run the training algorithm on the stuff on the left, and never ever let it see the stuff on the right. Then we're going to evaluate the performance of the output, of the learned model on the validation data, and that'll be a good estimate of how that model will do in future testing settings. So we would do something like this. We would build a table where we try different values of C, and maybe we would see for for C equals 0.001, maybe we get 0.91 accuracy on the training data, but then we see that we get 0.83 accuracy on the validation data. And then we try a bigger value of C, and we get even better accuracy on the training data and even better accuracy on the validation data, which means, we're doing good. And then we maybe set C to 0.1, and we get really, really good accuracy on the training data, like 0.99. We only make one error every 100 digits. But then our validation accuracy went down a lot, and this is a quintessential sign of overfitting when your training data performance is really high and your validation performance is dropping. And then maybe we try, just for good measure, we try C equals 1, where we get perfect accuracy on training data, but we get really terrible accuracy on the validation data. So this is a really good strategy, and this is pretty much what you're going to implement in the homework. But there's even better strategies if you have the time to invest in better evaluation of your learning algorithms. So what we've done here is we've just chopped off a bit of the data, right? In this case, in this image, this cartoon example, we chopped off 1/5 of the data, and we held it out, and we're going to use it to validate. What you can do is you can actually rotate which fifth of the data you hold out. So this is something called cross-validation. So maybe this time we hold out the first fifth of the data, and we train on the rest, and then we test on that first fifth. Then we hold out the second fifth of the data, we train on the rest, and we test on that second fifth. Then we hold out the third fifth and test on the third fifth. Then we hold out the fourth fifth, test on the fourth fifth, and then hold out the final fifth. And test on that. Then we can maybe average our scores across all 5 folds, and that'll give us a more robust measurement of the quality or the how good our learning algorithm operates for any particular parameter setting of C. And that's really good when you have time to do 5 folds, and even better is if you have time to do even more folds. If you can really, really in a fine-grained way chop up your data set, you can do something called leave one out cross-validation, which means you hold out only one example at a time. So this is a situation where we're holding out the very first example from our data set, and we're going to train on everything else. We're going to train on all n-1 examples, which will be very close to how our performance will be, right, if we train on all n examples. The only difference is we don't get that one example to train from. But then we get to test on that one example. We get to say, okay, did we get that one right or did we get that one wrong? And we try the next one. We hold that one out. We say, did we get that one right or did we get that wrong? We keep doing this on one example at a time and sweep through the entire data set until we get basically a count of how many times when we held out this one example did we get it right and how many times did we get it wrong. And that's going to be a really, really nice estimate of what our performance will be in future test data, because what we've done here is really get close to the true scenario that we're interested in measuring, which is where we train on all of our training data, with whatever parameter we finally settle on, and then we test on brand new, never seen before test data. Whereas with cross-validation is pretty good, but one thing that's going to be different is that if you have 5 folds, you're going to be training on 4/5 of your data, and that might change the behavior of your algorithm a little bit. So the more folds you do, the closer your behavior will be, and the better your estimate will be. But eventually, if you do n folds, you're basically doing leave one out. So that's the whole story behind validation. The idea is that we want to measure our performance on held out training data, which simulates the testing environment. And then we have different approaches for how we do this, but the overall goal is then this allows us to tune extra parameters like C that we don't want to overfit. We don't want to tune C to our training data, right? If we do that, then there's no point of C at all, right? Then we're just going to overfit for sure. But if C is like a trade-off parameter or some sort of parameter that prevents overfitting, then we want to tune that on held out data. Okay, and then when we hold out data, we can do different schemes. We can just hold out some data and just do one held out split, or we can rotate folds of held out subsets, which allows us to get a a more robust estimate of how our performance will be on future test data because we get more than one sample, right? For every fold we do, we get one more example of how our learning algorithm will perform. And then finally, we can do the extreme of that, which is you hold out one example at a time, which is the leave one out validation framework. And in that situation, you're getting a really good estimate of how your learning algorithm will perform because, right, you're training on n minus one examples, which is very close to n examples. Okay, so to summarize everything else we talked about in this video, right? Remember, I started with talking about MIRA, the algorithm, which is a more robust variant of perceptron. And the updates are very, very similar, right? When you go to implement this, the code is going to look almost exactly the same as your perceptron algorithm, except with the difference being that you're going to have an adaptive learning rate. So you have to add in that extra code to compute that tau parameter. And we're going to clamp the learning rate to prevent overfitting. We're not going to let that learning rate get too big. And because we don't want to do anything too drastic just based on any one example. So one thing to keep in mind is that if you get lots of examples that are similar, then their influence on your W vector is gonna accumulate. So it's not that, right, clamping C doesn't prevent you from learning if your data tells you that you need to learn this thing. It just sort of slows down. It sort of slows down the learning process to prevent it from going too far for any one example. Then we talked about validation, which is a general methodology to help you avoid overfitting to training data. And I talked about the variant of validation where we do cross-validation, where we do multiple folds of validation, right? We split the data not just once, but many times, so we get multiple estimates of our performance. And the extreme example of that is leave one out validation, where our folds consist of training on n minus one examples and testing on just one or validating on just one example. Okay, so hopefully that helps you get started on all the foundational pieces for the homework. You should have all the pieces you need for both the written and the programming homework. So get started on that, and of course bring your questions to class, to office hours, to Piazza, and to email. And otherwise, I'll see you in class.